Samples. Sample 1. Two identical light springs with force constant K1 are connected in series. The top of the spring is fixed and the bottom of the spring is hand connected by a body of mass m. Find the period of the oscillations. Let me check the spring constant first. When the two springs connect in series, does its spring constant are the same as the individuals or the difference? What we do, we assume this is spring 1, this is spring 2. Spring 1 with force constant K1, spring 2 with force constant K2. If you hand a mass m at the bottom of this spring, then we see both springs was exerted by mass mg. They are the same. So for the spring 1, you have mg equal to k1x. For the 2, you have mg equal to k2x2. Okay, so x1, x2, you can find this one. x1 equal to mg over k1, x2 equal to k2. And as a whole, we say this whole one is the big M, mg force equal to the new force constant. The extension is x1 plus x2. So x1 plus x2 equal to k over mg. We put x1, x2 in this one. So we get 1 over k equal to 1 over k1 and 1 over k2. In our case, k1 equal to k2. Okay, so the k, we want to find they are the same k. So the k equal to half k. The spring constant reduces into half k. All right, with that one, very easy. Okay, that be very easy to find the period, right? If the spring was cut into two at the middle, okay, then each spring, it has the new force constant equal to 2k. Okay, if you that's you can do this one. Now we go back to our question because all the k are the same. This k equal to this is half k. Then we go to period, very easy. It's 2 pi of omega. Okay, 2 pi m over k. This is the 2k, half k. So we get t equal to square root 2m over k. Okay? Sample. A line spring of less m and the force constant k is connected with a block of mass m. Its horizontal vibration has an angular frequency omega 0 square root k over m. Find the angular frequency after spring was cut into two at the middle and connect as shown in the figure. Okay, that's just a little bit complicated. Now let's first see this one. When the block move a distance x from the neutral position, it would exert two forces, one from the left spring, one from the right spring. So both are kx. Okay, kx. The question is, what kind of k it is? It is the same k as the original one before they cut into two, or they have the new one. From above sample, we know after they cut, the individual big K is equal to 2K. It's increased. It's 2K. So in this case, you get a 2K. All right, and you move one, you get another 2K. So altogether is 4K. And then the omega equal to 2 pi of K over m is 4K is 2 omega 0. 2 omega 0. Okay? 2 omega 0. Its angular velocity, angular frequency doubles. Example, a pendulum is formed by a thin horizontal rod passing through a uniform disk K of radius r and mass m at a distance h above the center of disk. Now, this is the point, horizontal. Okay, this is the center of mass. With the disk is radius r, and this point P is distance h from the center of mass. Okay, it's vibrate, small vibrate, theta very small. Find the period of the pendulum for small oscillation in terms of h, r, and gravitation for acceleration g. Find the value of h when the response period is minimal. Let's write the equation first. Look at the P. Around the P, we have I alpha equal to tau, right? The tau here is only the gravitational force, okay? We call it F R perpendicular. R perpendicular here is H sine theta, okay? When theta is very small, sine theta is approximately equal to theta. Here we have a minus sign. Why we have a minus sign? Because we think theta is go this positive in this case, and the torque is go this direction. So you have a minus sign. It always oppose the theta, positive direction. And then we see the alpha equal to minus mg over I h over theta. This is, you looked at acceleration proportional to displacement with minus psi with a coefficient. This must be omega squared. We put the I. What is I? The I around P of this disk is equal to parallel axis theory. The I come, we can check. Plus, you put all the mass of the disk around this P. This I is mh squared. So we get the I is I come plus mh squared. We put this one inside, we got omega. Omega squared equal to mgh over I. I equal to this one, right? Yeah. So we cancel out a 2 here, put up there, and we get this one. Okay, once we get the omega, we get a t, because omega t equal to 2 pi. Next, we want to find a time when the h can make the t is minimal. So what we do, this is a calculus. We dt dh set equal to 0. And we found h equal to r over square 2. At this moment, t has a minimum or a maximum. Well, from physics, it is minimal. We put it inside, we get a t. All these are mathematics, calculus. I'm not going to get into the detail. Sample. A pendulum consists of a thin rod of less m and an object of mass m. This pendulum is connected to a spring of force constant K at a distance h below its suspension point. Find the frequency of the system for a small oscillation, means small theta. Let's write the equation first. Tau equal to I alpha. For this system, okay, about C, we have tau I alpha. Alpha is the angular acceleration of theta. Okay. What is the tau? Tau is mg r perpendicular, this air sine theta. This is minus. Why is it minus? Because in this case, we thought theta is positive, is around the clock. And the torque is anti-clockwise. So you have a minus. And we also have force acting on this one. This is very small. What is this one? This one, suppose this is x, very small. So you have force minus kx times the distance r perpendicular called h cosine theta. So we have two forces to torque. This is minus 2 because this one force goes anti-clockwise. And we think the clockwise theta is positive. So this is a negative number. Okay? When theta is very small, this I is ml squared. Very easy. Okay? So we put this one inside. We get tau, these two terms, equal to I alpha. This is I is ml squared. Alpha is the second derivative of theta. When theta is very small, sine theta is approximate to theta. Cosine theta is approximate to 0, 1. We put this one inside, and at x, this x is h sine theta, is h theta. So we'll put these three in this equation. We get this is theta, x equal to h theta. This is a 1. x1, this is a 1 to alpha. And we rewrite it. The second derivative with respect to t, theta, equal to minus mgl plus kh squared over ml squared theta. Look at this. The angular acceleration proportional to the angular displacement with minus sign was constant. So this constant equal to omega squared. All right. So this is omega squared. Once we know omega, we know the t, because omega t to the 2 pi. This is the answer. Okay? And the frequency is the reverse of period. Example. There's a spring of force constant K between blocks M1 and M2 on a smooth surface, as shown in the figure. If block M2 is pushed by force so that the spring is less than its natural length by x0, find the maximum stretch of the spring after the force M2 is withdrawn. This is a pretty tricky question, okay? Now, we look at this one. We a force push it, so you have a original here, now it's got here, this x0 less than its natural length. And we withdraw this force, what happened? What happens first, it rebound, okay? A rebound to the original length. In this case, okay, starting this case, you have a V. This V, according to the energy, mechanical energy conservation of the system, we can calculate, okay? Calculate. There is force acting on this system, but this force, this point, the acting point, never moves, so no worse than on this system, okay? Okay. So we have originally potential energy half km squared equal to this natural length, no potential energy, and equal to kinetic energy half m2v2. We get a v. What next? Next is this move, a pull, a spring pull is lead. Okay, from that moment, there's no external force acting on the system. So what happened? Sigma f equal to ring. That means the linear momentum conserved. Okay, well, at the beginning, the velocity of two blocks are different. This fast, this slow, and gradually it extends to the maximum extension. What does this mean? If you stand inside, you see their relative speed is 0. They expand it, then at the maximum, they're going to shrink, right? So at this moment, there's no relative speed between these two. So they are the same. In other words, their velocity at absolute reference outside is the same. So what we do, we say, hey, hold this process from here to here, no external force, linear momentum conserved. Okay, and at the maximum stretch, V1 equal to V2 equal to big V. With that information, I would say linear momentum conserved from here to here, because no external force. That's the linear moment force. Okay, energy conserved 2. Okay, originally energy conserved equal 1. With these two, we can find the x equal to x0 square root m1 over m1 plus 2. This one is smaller than 1, so x is smaller than x0. That's natural. Because why? Because sum of energy is in them, kinetic energy. Okay?